In a previous video, we covered the difference between independent and dependent samples. And so if it would help you, you might want to go back and review that. But anyway, in this video, we're going to show you how we test for one mean, which comes from dependent samples. So if you recall, dependent samples means that there's some sort of a connection between the individuals in the one sample and the individuals in the other. And this is a notation heavy section, and so we want to draw a little attention to some of the notation before we dig in. We're going to use x sub I and y sub I to represent the individual observations in the matched pairs. And you could consider these like ordered pairs, even though they are listed separately. There's a reason that we're using x and y, because it is evocative of the whole idea of ordered pairs when you're plotting, say a function or something like that in two space. Anyway, we're going to be using d sub I to represent the difference between those observations. And as it says here on the slide, the subtraction can go either way. So sometimes they'll tell you what direction to subtract, sometimes they won't. But you always have to remember when you're testing with two samples that the test can be done more than one way. So you can do the subtraction one way and you may run it as a left-tail test, for example, and if you change the direction of the subtraction, it would then be a right-tail test, and so on. We're going to use d bar to represent the mean of those differences, and we're going to use mu sub d to represent the true mean of the differences, and s sub d to represent the sample standard deviation of those differences. And so very important whenever you launch on a new section, especially in this part of the course, you have to review the notation so you're clear on what each of those items means. If you're not, it makes it much harder than it needs to be. So anyway, in this video, we're going to do an example of matched pairs in action. Let's take a look here real briefly. As always, there are some conditions that need to be reviewed, and so this is as good a time as any to review those. Remember, we're doing two samples, but one mean, because we're taking the difference of those samples. And so we have to have random samples. They are matched, and so you can't change the order of the observations within the samples. It makes it a hassle. And we need the central limit theorem here. So the differences have to be normally distributed, or normal enough, let's say, if the sample size is small, which is less than 30. But if the sample size is big enough, 30 or more, then we're good to go, and we really don't have to worry about checking that. Anyway, here's our example. In this video, we're going to use the problem you can see in front of you on the screen right here, number 14, which is titled Car Rentals. It says the following data represent the daily rental for a compact automobile charged by two car rental companies, Thrifty and Hertz, in 10 locations. Test whether Thrifty is less expensive than Hertz at the alpha is 0.1 level of significance. And then they add a note there. Now, something you should think about, I've mentioned this before, and it's one of those things that should be repeated many times, because it's an endless issue. It never seems to stop being a problem. So if this problem had been encountered in a context-free setting, like say on an exam or on a quiz, how would you know that the process that we're about to show is the correct one to use? Because I'll tell you, it's very, very common to see someone field one of these problems on an exam where it's stripped of context, and they will use the wrong process. And since we allow you a sheet of notes when you take an exam, that's not a good thing. It means that you're not really understanding well if you trot out the wrong process for a particular problem. And so what is it that makes these matched pairs? Well, you'll notice that each of the observations are connected because they're taken from a certain city. So Chicago, Los Angeles, Houston, and so on. And so we would expect that if you encountered this in a context-free setting, that you would notice, hey, wait a minute, this is a matched pair situation, and so I have to use a t-test, and so on and so forth. Anyway, let's take a quick look at the framework that we have to work within. So for testing matched pairs, again, there's two samples, but there's only one mean which is going to be tested. And the reason is because we're taking the difference between the samples and we're actually working on the difference. So you can have a two-tailed test, a left-tailed test, or a right-tailed test. Notice that the null hypothesis is the same in every case. It's effectively a claim that there is no difference. In other words, mu sub d, the true mean of the differences, is equal to 0. And the only thing that changes is the alternative hypothesis. And so when you read a problem like the one we just looked at, obviously the first thing you have to decide is, well, what way am I going to run this test? Is it going to be a two-tailed test? Is it going to be a left-tailed test? Is it going to be a right-tailed test? And so on and so forth. And so believe it or leave it, but that can be kind of slippery when you start to look in situations where you have two samples like this. Now, rereading the problem here, there is a crucial phrase which we hope you're going to notice. It says, test whether thrifty is less expensive than Hertz. And so that kind of gives us an insight regarding where we're going to go from there. So they're asking us to test whether thrifty is cheaper or less than Hertz. And so if you were to treat this as an inequality and you were to subtract Hertz from both sides, you would end up with thrifty minus Hertz is less than 0. And so if we're going to use x sub I to represent thrifty and y sub I to represent Hertz, which, when you look at the table that they've given in the text there, that's sort of a natural choice. Then if we do d sub I is x sub I minus y sub I, we are doing a left-tailed test, as you can see here. So in other words, we would expect that difference would be negative if thrifty is less than Hertz. And so we should be testing mu sub d less than 0 for the alternative hypothesis, as you can see there. So obviously we want to get that data keyed in to the calculator. Let's do so. So if you like, feel free, pause the video and key it in for yourself. We're going to just be needing the data from the table right there, and obviously we're not going to be entering the city names. We're just entering the data in the thrifty column and the Hertz column, and we'll take care of the rest in a second here. So as you can see, I've already taken the trouble to key in the data, and so I have thrifty in list 1 and I have Hertz in list 2. And we said that we were going to do thrifty minus Hertz. And so to construct that, you'd go over here to list 3, and you go up to the top of the list, as you can see. And you want to select that, and then you press list 1 minus list 2. And there are your differences right there. And, it's always good to kind of take a look at that a little bit. It's hard to say whether we're going to, or how we're going to run, how we're going to conclude from this test. We have a mix of positive and negative values there. So anyway, as you can read on the slide, we're going to use a t-test for this. So in the same way that we ran a t-test in a previous chapter, we're going to use a t-test here, or a t-interval, would be equally good. You might have caught on a previous slide there. Let me show you again. You have a choice when you do this, whether you're going to test using a hypothesis test or a confidence interval. And we would expect that you could field this kind of a question going either way. And I'll show you both in this video here. But anyway, let's go back to the calculator. We're going to be using a t-test here. And so once you've taken your differences, normally, for a small sample like this, we would want to check normality. And so if you've forgotten how that goes, it would look like this. You want to get out of here, and you want to go up to the stat plot, and you're going to need to turn on one of those stat plots. So plot 1 is good. As far as the type is concerned, usually you would look at 2, right? You would check this one here that's flashing, because that will show you a box plot with outliers, and we don't want outliers. And you're also looking at a normal plot, which would be the very last one here. So let's do those in reverse order. And even though the problem said we don't have to, we're just doing it for the sake of thoroughness. So our data that we want to look at is in list 3, and so that's good. Everything is good here. And so really all we have to do is get it on the screen. Let's quit this, and we'll do zoom 9. And as you can see, there's the normal plot. Now it looks more or less okay. I mean, you might notice this point that's out here towards the left-hand side of the calculator screen there. Does that make us nervous? It does look like it's sort of out of alignment with the others, but you have to remember when you visualize one of these normal plots, you have to think about how they would appear if you had those 95% confidence bands around them like you see in the text. When they generate one of those from Minitab or SPSS, and the confidence bands widen up around the extremes. And so in this case, I would say I'm comfortable with this. The box plot makes it more comfortable, so you can also look at that. You can quit this and go back to the stat plot and then change that. That's the one we want right there. And so the data is in list 3. That's great. And so you can quit this and then do a zoom 9 once again. And looks okay. It's not exactly normal. It's not perfectly bell-shaped, but it's normal enough for what we need. And so I would be satisfied with this. Anyway, let's run the test. So we need to get out of here, and we need to go back to the stat menu and to the test menu, and we're looking for number 2, which is the t-test. And so as you can see, it has 2 different modes. It has a data-driven and a summary statistics. We want the data-driven mode, and mu naught is 0 in this case. That is from the null hypothesis. And the list is in, or the data that we're testing rather is in list 3, so we need to make sure to change that. Don't change the frequency, but it looks like we will need to change the alternative hypothesis to a left-tailed test as we had set. So at that point everything is good and we can run the test. And we definitely want to write down our results here. So as you can see, I've recorded that I'm performing a t-test here. We definitely want to know that because, well, believe it or leave it, but people often do use the wrong test. And so we want to make sure that we're playing that that's the one we used. You can see the test statistic recorded there. That's always good because that tells me whether or not you keyed it in correctly. And then finally the p-value. Now, if you recall from the problem, as you can read, we were told to use alpha as 0.1 as our level of significance. And so as far as a conclusion, the p-value is larger than the level of significance that was given, and so we can't reject the null. So what does that mean on a practical level? Well, it means that the evidence we have does not support the claim that Thrifty is cheaper than Hertz, and so we probably would want to write that down as well. Always good to have a practical conclusion from one of these tests as well, especially if you can deliver it correctly. That really gives you a tremendous amount of credibility. Anyway, this can also be tested using a confidence interval, and so I think I'd be remiss if I didn't show that. So if you remember, the level of significance and the confidence level are related in that the confidence level is 1 minus the level of significance. So here we were told to use 0.1 for our level of significance, and so 1 minus 0.1 would be 0.9. So in other words, we should be using a 90% confidence interval, a 90% t interval, in order to do this using a confidence interval. Let's show that. So we're back here at the calculator, and everything is pretty much in place. All you have to do is get out of here, go back to the stat menu, go to the test submenu, and a t interval on this calculator is number 8. And so you can select number 8. You can see that everything is good to go. The only thing that has to be changed here would be the confidence level, and as we said, we would be using 0.9. And so if we calculate, there's the result right there. And notice that the left endpoint of the interval is negative, whereas the right endpoint is positive. And so that means that the interval contains 0. And so, in other words, that suggests that we are 90% confident that the null hypothesis, which was that mu sub d equals 0, is plausible. So we probably should jot that down as well. So as you can see, 90% t interval. And so that tells me a couple of things. It tells me the level of confidence, so it shows that you know. It also shows that you're aware that we're supposed to use a t interval. And you have the confidence interval written down, or I have the confidence interval written down right there, and that shows that I did it correctly. because the numbers would match with the correct answer. And then I have a conclusion. It says, since the CI, confidence interval, contains 0, we are 90% confident that mu sub d equals 0 is plausible. So in other words, we're not rejecting the null. Hope that helps. We have another example for you in a different video. Please check that out. And if you have any questions about this one, feel free to drop me a line.